and all the webinars are recorded and then are sent to the UG2 and hosted on their YouTube page. So if you want to send to your colleagues and go back to this, you can find it on YouTube later. The first one we had the first webinar we started, we had almost 100% coming, and it's stabilized since then to 20 or 30%, which compared to 100 can seem not a lot, but is already a good um, a good number, especially that it's people that are different people every time. So basically, we can attract the people that are interested in the topics we have. That's interesting. And the announcement I would like to make is that we have recruited someone to coordinate the Ego network. Right now, I was doing it a bit on the side, and we managed to secure some funding, and we'll have a new person that will come to do the coordination and try to expand what we are providing, what we're doing. And she will start in January for 24 months. So that's a very exciting news. We'll get more in touch with what UG2 is doing and Georgia. And we've seen that with Georgia coming, UG2 has really risen and become more attractive. So we are hoping to do the same, and we will be working together closely to stimulate the network and the community. So that's something very nice and motivating. So you will hear more from Ego very soon, and hopefully you're excited as well. So I believe that will be my last time I will be sharing a webinar, because next time it will be her. I will still be there, but I hope that you will accept her, and that you will be enthusiastic as well, and that we will make great progress together. So that was the news that we have, the exciting news, and that can with that said, we can switch to the today's webinar that is about glider simulators and digital twins. We only have two presentations, so we have time for questions. So really do not hesitate to ask for questions. They are really kind, and they can give a very interesting answers. So please, we're here to start a dialogue. So please be active. That's what I would say, even if it's close to everyone's thinking of the last gifts that you have to purchase before Christmas. We still here have 1 hour together. So the first presentation that I have that will be presented will be by Lucas Merckelbach. So he sent me a little presentations, a little description. So he's Dutch, working for the German Helmholtz Research Center in Hereon in Hamburg. He's a civil engineer by training and did a PhD in mud in Delft, a postdoc on turbulence-induced reflections of acoustic waves by sediments in Jos in the Netherlands. And he started working with gliders at NOC in 2007 as a postdoc, and he's still working with gliders. And now at Hereon since 2010, and he's the author of DBD Reader, a fast Python module for reading Slocum gliders binary files. And he will present the glider simulator that he did at Hereon. And Lucas, the floor is yours.
Thank you very much. Then it's always the moment of truth.
It worked 2 minutes ago, and it's working now, so it's perfect.
Okay. Except that I don't see it myself because
Yeah.
I am not so great. That is How do I do that? Is that I see it very small?
Yeah, I see it well, but
Okay.
I'm
Well,
wondering
that's
if the sound is really good. Alvaro, do you hear well, or it's a bit lagging?
No, it was working before, but now it's lagging, Lucas.
Okay.
it's not good. The only thing is
Maybe.
I don't see my slides so well.
Yeah, that's a problem.
That's a. If you want, I can share them.
Oh, no, it's okay. Got it. Yeah.
You got it? Okay.
Yeah.
Okay, so we can hear you. We can see the first slide, so it sounds okay.
Éviter toute la partie.
That goes away. Okay, so welcome everyone. So I go back one slide. Then, so my name is Lucas Merckelbach. I work at the Institute of Coastal Dynamics in the Helmut Centrum Hereon, based in Geesthacht, which is a town near Hamburg in Germany. And I will talk about glider simulators and digital twins. So because some people might not have heard about Hereon, I thought I'd devote one slide on what we are. So it's an institute that is focusing on material research and coastal research, and it's part of the Helmholtz Association in Germany, which also contains institutes like ARI and GEOMA that you might have heard of. We're about 800 people in total, and the majority of them work in material research. I listed a few institutes there. There's many more, but that's not of relevance today. So we're in coastal research, and I'm in the group of coastal dynamics. So the question, why do we want to have glider simulators? Well, the reason for that the reason why I developed a glider simulator is basically because in 2011 we started using gliders in the North Sea, in the German exclusive economic zone. There are lots of ships, offshore wind parks and fisheries and all these things, and also the EEZ is not a no man's land or sea, if you like. So it's very regulated, and Germans like that very much. So that's the national sport rules and regulations. So that means that before we actually can deploy our gliders there, we have to comply with a lot of rules there. So one of them is that we need to apply for permission, and a requirement for getting a permission is that we commit ourselves to make glider trajectory forecasts for 12 hours, every 12 hours during the mission of the glider. And this is needed to essentially have information ready that will be sent to the vessel traffic control centers that distribute that information to ships in the hope that they will avoid this region where the gliders are there. So a glider simulator basically simulates the whole thing about a glider, and that constitutes of a model of the glider software, a model of the glider hardware. So then we have basically the glider software and hardware covered. Then we need to know how this glider works in the ocean. And the last is that we need a model of the ocean itself. So all the software I wrote in Python, and it's available on GitHub. And also, I limited myself to Slocum gliders because that's the only type that we have. And yeah, so that's the only need that we had at the moment. So the problem with modeling the software is that the source is closed source. So we can only guess how it really works. There are quite a few assumptions to make about what a glider actually does. But I think it's a stack of finite state machines. And the reason to think that is that if you look at the log of some glider, then you can see here highlighted a number of words like 1, 2, 3, and so on, and they have the behavior names in there. So it's the word ending behavior at the top, then a 2 by 3 surface behaviors, a go to list behavior, yo, and so on. And each of these behaviors work like a finite state machine. A finite state machine, it's called finite because the thing can only be in a finite number of states. In the diagram that I have here, it's 4, so A, B, C, D. And every state there's a transition table. Basically, it means on which condition the system will change from one state to the other. And it can be that, like, you have a cycle like here, S from SA to B to C and D, but you can also go, in this case, from B to D, and also, for example, that you can stay in the same state depending on what the input is. So the glider software model is built off a stack of these finite state machines, and they are being read by from the mission file and all the MA files that come with it, and it builds up a stack like you've seen before. And that basically models the whole thing. I don't want to go in too much detail about how I do that. I think it's not the purpose of this. It might get a bit complicated. So when we go to the hardware, so that's the part where the software drives the modeled hardware, and we have in effect 3 actuators, like the pitch motor, the buoyancy pump, and the fin. And this is relatively a simple part. We can say like a commanded value, and then the actuator will move to the measured value in the same way that a real pitch motor would do that. And how this responds, we can actually see that from the glider data, and we calibrate all these models with those actual glider data. Then we need to know how the glider actually behaves in the water. So we need a model of the glider dynamics. Again, what comes into play is the pitch motor, buoyancy pump, and the fin. They basically are the input of this model, including the density and the environmental velocity, which will be discussed in the next slide. But at the heart of this model is the flight model. Basically, the buoyancy pump together with the density gives you the velocity of the glider through water, including the angle of attack. And that means angle of attack is the angle that the glider makes in addition to the pitch angle. In the diagram, that's the little alpha, and theta is the pitch angle. So this is a model that gives you how the glider moves in the water. And we need an additional piece of kit, so to speak, because sometimes a mission might say that we put a battery position at a specific, the battery and the pitch battery at a specific position. And then we also need to know how the glider behaves to that. So to that end, we have a nonlinear regression model which includes the pitch battery position, the buoyancy engine position, and also the pressure, and relates that to the pitch angle. And this data is usually obtained from some calibration data that we do at the beginning of each mission. The details are found in, for example, a paper that I put on the bottom of this slide, published in Geoattack in 2019. And lastly, we need a model of the environment the glider is in. So this environment should produce a velocity in horizontal directions, like eastward and northward velocities, as well as the density. And the density goes back into the flight model. and the velocities are used to add to the glider velocity to create a vector that basically lets the glider move into space, or in space. So the coordinates that we need is latitude, longitude, the depth, and the time. So what I've done in the past is I used a getter model that is run in-house in our institute. This is kind of an operational model, and I could get the forecasts from that model and put that basically into my model, my glider model. For another purpose, I used output of the Mercator model that was in the Adriatic Sea. The problem with models is that sometimes they break, or there's an issue and they're not run, in particular with the model that we run in our institute. So that I moved to glider data based environments. So essentially, I used the most recent density profile as input for the density, and I compute depth average water velocities from the water velocities that the glider reports. And this is done in combination with a Kalman filter that includes the tides and a residual current. So I also get the change of the currents in between two surface times that the glider does. So if the glider comes to the surface, say, every 4 hours, then I have the varying time, the varying values of the current in between those times. And this is also described in a paper that is listed down below. So if we put that all together, then we get something like this. On the left, we have the doc server with the, for Slocum glider users, the known directories, to glider, from glider, logs, and repository. And on the right, we have this collection of models, like the software simulation, the hardware simulation, the dynamic model, and the current simulation. And how this works is that the information for the flight model can come from the density profiles, for example, or from external place where if you have a numerical model that you can access. And it also takes the GPS positions and time to start the simulation. And it's also important to get access to what files are currently on the glider itself, the mission and the auxiliary files. And for that, I didn't mention that now, but I'll do that here. I have like a solution for that, which we call MA tool server. That is a way to edit these mission files for gliders, and they are then stored in kind of a repository that can also be accessed by other programs like this glider simulation tool. And on the bottom left, I gave the references where you can find this software on GitHub. So, and as I mentioned in the beginning, that one reason of doing this is that we need this information sent out to vessel traffic centers. So that's the last part of the glider sim box on the right of the screen, that we collect this trajectory, or we collect this information, make a box around this trajectory, and send that as an email to the authorities. So the future use of this glider simulator might be in a project that we submitted recently, and we hope soon to find out if that gets funded or not. And this project is about the marine autonomy in the Arctic-Baltic observing systems, and a digital twin approach to that. So what is aimed in this project is that the gliders are ideally prepared to be flown under the ice, where they don't have immediate contact to the surface. So it's impossible for them to offload the data every time they come to the surface. So a way to get around that is to have like a buoy here, which does have expression to the atmosphere, that the glider goes in near this and then offloads the data there so that the data can be transmitted. An alternative use would be if there's instruments on the seabed that don't have an expression to the surface themselves, that the glider goes there, picks up the data, and goes back to where there is only water and then can be transmitted. This proposal consists of a number of digital twins. One is specifically about the acoustic communication protocol that is envisaged to be used by the gliders and for example, this buoy. This twin of the modem itself, of the glider platform, and that's basically what I've been talking about today. That will be the core for that. And all of this will be integrated in the European Digital Ocean of Twin of the Ocean, AD2, which is a big framework where projects like this can be embedded in, and then hopefully when picked up by stakeholders, it can provide a way to plan missions to get gliders working under the ice and provide data to models where now there are no data available. So the conclusions. So we have developed a glider simulator, or you might call it a glider digital twin. And we use that to make 12-hour trajectory forecasts for gliders in a mission in the North Sea. And we will use this framework as a basis to make a digital twin of the glider in this Mabos digital twin project if it gets funded. The software that I used for it and wrote for this is available on GitHub and is provided as is, and I take no liability for any loss and this kind of things. But yeah, so the links of it are on the slides if you want to access it. And there I will end my presentation. Thank you very much.
Thank you very much. It was very clear and very insightful. Are there questions? We have some clapping from Pierre, from Julian. And Pierre, you have a question? First one.
Yes. Hi, Lucas. Very nice presentation. Did you make a kind of assessment of the accuracy of your model using taking back the data?
Yes, I did actually. I wrote a report on that as an evaluation of this whole thing. And I looked at two things essentially. One is how well the model predicts the behavior of the glider. So it's essentially, how well does the glider follow the model? How well does the model follow the dive profiles, for example, that are then actually measured, or that you can plot from the binary files? And the other thing is, if you compare the track of the observed glider tracks with the ones that are being predicted, the first part is actually pretty okay, I think. And the second part is depends on a few things. So the forecast assumes that you don't make any changes during this 12 hours. And this is not always the case when you run such a mission and you look at the data during the day, and you think, oh, maybe we do something different here or there. That can sometimes lead to significant changes. But the biggest source of error is actually the how well you can compute the current of the ocean. And the models that I've used.
I don't think you should be outside.
The models I've used to simulate the flow in the North Sea are okayish, but not always that great. So there's a margin for error there actually, and I think can't really exactly remember, but it's the order of a few kilometers, like 2 or 3 kilometers that that the glider can be out of the box that I actually promised it to be in occasionally, but it's not so bad actually.
That's good, yes. Okay, thank you.
Thank you. Are there other questions? Because I have some.
So
I wrote down. No, the first one I have is that it's really interesting to see and to test, because I remember that during the BioGlider project, where we had the Sea Glider with both UVP at the front and EK80, it became very heavy, and and they had some difficulties to steer it. And I imagine that with the glider dynamics, the model, and that you could kind of see it. I don't know how you, and the question I have is how you calibrate the dynamics with all the different sensors. If you have to calibrate the model for every mission, or if it's something that's general.
yeah, so no, I think you cannot calibrate once and then hope it works for all settings. So typically what we do is that we devote some time when we deploy the glider to make some decent dives. So in the North Sea, that's only 40 meters deep. So what we typically do is that we collect like about an hour of data, and then be able to send the high resolution data back to shore, and use that to calibrate the glider. Or the glider model. What we calibrate usually is the drag coefficient and essentially the density of the glider. So normally you set the volume and you compute the mass, or you compute the volume if you set the mass. It doesn't really matter, but you need to set one and then you compute the other. So essentially you compute the density of the glider. So yes, you would need that. That would then tell you probably that if you have lots of things attached to it, like this camera system, that the glider would not fly very well. But you also know that by the time you've done this calibration dive. So that is, the prediction is a bit limited, I guess. And also one issue you might have with making changes to the glider itself is that you how do you say that? So you might, for example, get like some oscillating behavior of the glider because of get instabilities or something like that. The model will not tell you that. So the model itself only looks at the vertical and horizontal force balance, and doesn't look at the torque, because that is actually not really needed. I do that with this regression model. It's much simpler. But how the glider actually would behave dynamically, this model will not tell you that. I'm sorry.
No problem. Okay. Do you know if other groups are using it? And also, are you using it for all your missions, or do you have some missions that are outside of the need to have the 12-hour forecast, but you still use it because it's convenient?
Well, I use parts of it. I use this this MA tool server thing. That's our way to pilot a glider with more people. So the way it's set up basically forces you to, when you change a mission file, it forces you to write what you've done. And this is all logged and then sent to a list of email participants that are interested in this. So everyone knows what is happening. And also it gives you kind of a history. So at the end of the mission, you can put it all together and you have half your cruise report written already. So that part I do use. The dynamic model I use also during the deployment, essentially. So I use that to do the fine tuning of the ballasting if the weather permits that. So if we need, so we make a dive and then the model computes how many grams or too heavy or too light the glider is, and then we do that on the spot. Yeah, and when we do measurements in the North Sea, because then we have to, but otherwise I would not use it actually. Because the trouble to set it up is quite a bit, in particular to connect that with an external model, for example, for your currents.
Okay. Okay. And last question I have, I don't think if people have questions, please go. But I have one question: is that you've developed it for the Slocum, and is it still on for Mabos, only aiming at Slocum, or it tried to open it?
So what is Slocum specific? Well, the dynamic model is to some extent glider specific. In the sense that you define your drag coefficient and lift coefficients and all this kind of things. Apart from that, there's nothing that ties it really to a Slocum glider or a Sea Explorer or anything like that. So you would need to do a small investment in figuring out what those coefficients are, and then you're good to go. I think I cannot really answer that because I don't know how any other glider works. But I think the key part to change is the simulation of the software that runs on the glider, because I can imagine that is quite different. If it works more or less the same, maybe you could emulate the way one glider works with the MA and MI files. So you can try to translate it. I don't know if that would work. I would need to know how the other gliders would work in particular. But I think it's probably easier to write that part from scratch.
Okay, thanks. I believe we can take Jérôme and then move on to Alvaro.
Yeah, hi. Thanks, Lucas, for the presentation. It's probably a newbie question. We are not yet very used with gliders, but could you, on your slide where you had this geometrical description, can you explain the difference between you had the theta and the alpha angles?
This one, you mean?
Yeah. What is I've not caught what is I think the alpha angle.
Okay, so okay. So I stole this picture from the paper which is on the bottom of the screen. Basically, X and Z is a reference frame fixed to the Earth, and eta psi is the reference frame related to the glider itself. There's two ways of looking at it, essentially, but it comes down to the same thing. But so depending on the status of your buoyancy engine, you will have a net vertical force as being the buoyancy force minus the gravity force. In this case, it's the yellow vertical line vector. That is, the glider is put to climb, And because of moving, it will have a lift force FL and a drag force FD.
Okay.
Yeah, so and the theta is basically the pitch angle as measured, but the glider will move, in this case, when it goes up, a bit steeper than that. And that's the angle of attack, this alpha. And
okay, it's a kind of drift, of drift, yeah.
well, yeah, well, it's basically that you have to put your wings on a small angle for them to provide lift.
Okay.
Yeah.
Okay, thanks.
Yeah.
I was looking also, the alpha is really the small one, the small angle.
Yeah.
That we have. Okay. Well, thank you very much, Lucas, and fingers crossed for my boss that it's funded.
Yeah, we'll figure out soon, I hope.
Yeah. That's good.
Sharing that. Yeah. Okay. Good.
Yeah. And now we can move on to the next presentation from Alvaro, which is also about Slocum and also about digital twin, and see how you can develop two things that have the same name but are totally different, or at least a bit different. That's and
Thank
it's
you, Yves.
also and maybe it will help grasp a bit better what a digital twin can have behind.
I start with the philosophical bit. Give me just 1 second to share my screen. Right. I put in presenter mode. Can you see my screen?
Yeah.
Okay, perfect. Yeah, so my name is Alvaro Lorenzo Lopez. What's my title today? A senior delivery lead on autonomy. I work at the National Oceanography Centre in the UK. I'm based in the Liverpool Centre. And within the NOC, I work in the National Marine Facilities on the robotics division that is called Mars. And yeah, my presentation is about digital twins. This is a project called MASDT. MAS is the acronym for Marine Autonomous Systems and Digital Twin. I'm going to start a bit, as Yves has said, philosophically on what is a digital twin. And if you work with digital twins, on every conference you go, this gets discussed all the time. And I think there is a proliferation of the term at the moment. We will consolidate a definition, but this is the one we're using. And I'm taking this from the IMFE. You have which is the I can't remember. It's a framework for environmental digital twins that is being designed in the UK a couple of years ago. And the definition is just a bit that I'm going to focus on the bit that is in bold. A digital twin is a virtual representation of an object or a system, for example, the natural environment, and updated as the system changes using observations. So under this definition, we can have three kind of blocks. You can have a digital model, which is completely decoupled from the physical system. It's not connected. You can have a digital shadow, which is taking data from the physical system and simulating the dynamics of that physical system. And finally, the definition of the digital twin we're using, you have a physical system, a digital system, and they are connected both ways somehow. So that's the definition we're going to use. But I'm going to go now a bit on the why we apply for this project. This project is under a program funded by the National Environmental Research Council called TWINE. And we put the proposal, I think it was September, October of last year, and basically was awarded to us this year, just before we went into the Christmas break. And it's a program to develop kind of prototypes of environmental digital twins. I think 4 or 5 projects got funded. In fact, Julian, which is in the audience, she's co-leading one of the projects on that program. And they are all similar but different. So ours is trying to solve some issues. One of the concerns I and people in my organization are having is what is the future of serving systems? And one of the things we are discussing in the UK, and there is a program called FMRI, Future Marine Research Infrastructures, is how this looks in the next 5-10 years. And our working assumption is that the number of autonomous platforms is going to increase dramatically. How dramatically and how quick that's going to be is going to depend on funding and strategies, but the numbers of platforms is increasing at the moment. Maybe slow, maybe, but yeah, it's not a matter of if, but it's a matter of when. So in this picture, kind of, I have some of the UK research vessels and a combination of multiple gliders, cargo profilers, mooring. So there are going to be a lot of yellow things in the ocean. So how do we scale up systems? One of them, I have here a very, very silly cartoonish way of explaining how a glider mission works. So you start at the beginning with enthusiastic PIs and pilots, and the PIs ask the pilots to do things, and everybody is happy to do it. Then scientists, obviously, they are driven by curiosity and they keep changing and asking to do more things. But the pilots keep making changes, getting tired. At the end of the day, if you do that all the time, it can be very time consuming. I mean, this is an exaggeration, of course, but it's just to give you an idea of it. But also, it's not just the interaction between the scientists and the pilots. You also have to babysit the yellow things. And while they usually start behaving properly, then as the missions progress, they start misbehaving. And yeah, after if you have multiple of these in the water and you have multiple pilots, at the end, it can be a bit nerve-wracking. And this is just on some gliders in the water. While things have dramatically changed when I started, since I started working with gliders in 2009. And back in the day, we were happy putting a single glider in the water. Pierre and others were already hinting the use of fleets on some experiments in the Mediterranean and other areas, but a single glider was common. These days, we as a community, you put 2, 3, even 5 gliders, but still, if you go back to that vision I show you, when we're going to have hundreds of platforms in the water at any given moment in time. All these things making changes on the glider, keeping an eye on them can be time consuming, and you need a lot of resources. So the challenges we wanted to address when we put this proposal in were some of the ones that we have here. Is how we enable researchers to have more control of glider operations on projects while retaining pilot accountability. There are a lot of models of piloting, you can see some of them. So in the UK, we have, where I work, I know we host the National Mining Facility, so we have a centralized model, but universities in the UK and groups also can have their own labs with their on vehicles. But in any case, if you grow a critical mass, you are always going to have that differentiation between pilots and operators, because if not, your scientists are piloting all the time. So make the operation of increasingly complex glider missions more efficient for glider pilots. Again, if you have more gliders and more complexity on what you want to measure, it's easier to make more mistakes. If there are longer missions, also people get tired. So there's a lot of load into the pilot. Increase the value of glider observations to operational models. So I'm going to show you an example in a second, but we're starting to see modelers more interested on using glider observations to improve how the models work. So we're thinking, okay, can we also factor environmental models on operations to make more efficient and close the loop? And then finally, from a technical point of view, it's like, if we want to scale up these systems, how we make these digital twins or systems interoperable. So to frame all these challenges, we found a use case to frame our project, and we decided to have we're doing operations constantly at the moment with the Met Office. So NOC is operating gliders for the Met Office since, I don't know, it's been for 3 years. So it's a glider all the time in the North Sea. It's an area where they lack observations to validate their model. In other areas, they use cargo profilers or have shifts of opportunity, but in these areas, there is an scarce, they don't have ways. So they've been putting gliders. At the beginning, there were two all the time, and then there was some issues. Maybe I'm not sure about probably funding, and that now is one all the time. You have there the link of the operation of the current one, Mowgli 9, which Mowgli stands for Met Office glider or something like that. And yeah, they are all the time. And what that operation does, and I should have had assumed there, is that they want observations on that area, but we have decided, or at least being agreed with the pilots, that basically the glider is doing a pattern within in between 3 waypoints all the time, contained on a box where any observation on that box is acceptable to basically help them improve the model. But one of the things we're speculating when we were putting this project is, okay, so the limitation may be that if you want to make more changes to make the glider to visit more areas and improve what you're doing in that box, you need to be hassling the pilots all the time. So this is a good compromise. What they've done is just decided to do those 3 waypoints, and they keep repeating. So we then said, okay, why don't we have a project to try to start automating the operations of gliders on that area, and that help us to build digital twins that, as following the definition I showed you before, we can connect models with observations, have the models controlling everything. How can we put that together? And we came with this concept. We have 4 boxes, kind of, plus a glider. In the top left, we call objective generation. So this a UI for scientists to design missions. How do you want your campaigns to be at a high level? If they want to sample, in the case of Mowgli, maybe some experiment, or you may want in other contexts to sample a thermocline somewhere. But it's for scientists to interact without necessarily having a lot of knowledge on how to operate a glider. Then at the bottom left, we have our modeling, our case. At the moment, the glider data gets assimilated on the AM15 model from the Met Office. And so what we're getting from the model are ocean currents, and what the Met Office called innovations, which I believe are the deltas between what the model was estimating and the measurements of the glider. So we can see how measurements are impacting the model. So what we are going to do is try to start automating the operations. So we partner with the Oxford Robotics Institute, and they have designed a mission planner. Originally, they were going to design a mission planner to automate some of the operations with the glider. I will tell you exactly what we operated in the end. There was a big space when we started. And finally, you have the mission execution, which is where you receive all the plans and they get translated and get sent to the glider, so the glider gets operated. And to glue all this together, we have an interoperable integration layer that we call communications backbone. That is the core of our system. Is what will allow us to use different autonomy engines, different objective generations, different mission executions, and assemble different digital twins. This is just a small exemplar, so we're using this project to build the components and build all those arrows. I'll show you a little bit more of detail. So the objective generation, I'm showing here some of the UIs we are developing, and this is all about human interfaces. How a scientist or even a pilot goes and define which areas they want the autonomy to be operating, what are the exclusion zones, inclusion zones, how to make transects, what to visit, and including narratives. So it would help to do the communication within the team. It's a little bit similar to what Lucas described on his simulator on how the changes on the MA files, but at higher level is basically campaign design. I'm just showing you 4 slides of the UI. I have a bigger presentation on the process. If anyone is bored later, I can stay and go walk through it. But yeah, it's just here you have the landing page where basically on the left you will have the group of operations you're defining. On the right you have contextual help, and you have the map to start defining things. The second slide is already it has already defined an inclusion zone, where basically your area of operation, and you can see features that is showing. So when you click, it shows all the different features you have added to the map.
Alvaro,
The next one,
just
yeah.
few minutes, please. Few more minutes.
Do you want me to go faster?
Yeah, it's maybe a bit.
Yeah, sure. No
Thank
problem.
you.
So I will go to the next one. So the next one is the mission planner, developed by the so the Oxford Research Institute, and this is basically defining. It does probabilistic planning, and it uses actually Lucas dynamic model and currents from the AM15 to calculate where the glider should go. If you want the glider to go to a position, what is the most effective next waypoint to target to basically have the most optimal route. One of the most important things we're trying to resolve with this is building trust and accountability. So one of the things that we've done, and Ben on the call did, is design how you connect what results can the mission planner send to the client. We're not allowing a mission planner to change every parameter. We have a matrix of predefined missions that the mission planner can run. This way, we can assure that the pilots can design what is acceptable and what is going to hit the glider is safe to run. So the pilots can be sure that it's safe to run, and we are sure that the results are, the mission plan can go wrong and basically plan anything and send anything to the glider that could break it. And we're also building an adapter in our architecture, which is basically the way that we connect to the dock server. This is to show you a lot of arrows of how our architecture looks. Is a bit complex, but the most important pieces to understand is this communications backbone that does integration of different things, different components. Our C2 is our piloting infrastructure, the autonomy engine, and then that SSFNC adapter is the piece that connects the gateway, the integration layer with the dock server. We're developing this, or most of these components, on open source. So our communications backbone is available on our Open GitLab. If you go there, you will get the previous version we developed. So by the end of this project, we will release the current version. And one of the things we do is we provide a packet of software, which is the backbone itself. It's a RabbitMQ based system. And we provide a lingua franca for that system. So basically, we're decoupling how you talk with from the communication channel, trying to make easier to integrate these systems one with each other. And you have the link there and the URL, but I'm happy to talk to people later if they want to contact me. So showing some early results. So we have the system fully integrated at the moment. So we have the autonomy engine sending plans using the messages and the backbone. They're hitting the glider already, and the autonomy engine is co-piloting the glider. So while the pilots decide a lot of the parameters, the autonomy engine is changing the targets on every surface. And we have some preliminary results on how the transect looks with and without autonomy engine. We still don't have enough numbers to see that this is statistically relevant. So while it's looking good, it seems to be making the line straighter. We can't still say that it is working. So we're going to be running it for longer until we can claim that it's doing what it should be doing, optimizing. We're going to run an experimental phase starting at the beginning of the year. I think it starts in January, where we will have the UI finally prepared for the pilots, sorry, for the scientists to use it, and we'll integrate different products coming from the model. So the idea is that scientists will decide experiments to see how to improve the observations into the model even more. So yeah, finally, some conclusions. Building complex systems like digital twins is just complex, and you need to start very small and do multiple iterations to fully understand the problem, to get user trust, and users means stakeholders, your scientists, your pilots, and you need to iterate to tune the solution. There is no, you are not going to get it right the first time. We are trying to build our interoperability and openness from the beginning. So as I said, most of it is going to be open source. And this is just a small twin. It's just the first of hopefully much bigger projects or other projects. And we could reuse these tools in the future to keep the trajectory. Yeah, integrating more AI in all these systems. And that's my presentation. If there are any questions, I will be happy to take them.
Thank you, Alvaro, for putting a lot of context around this. How long is the project, and how much time did you have to work on it?
Yeah, so started in January and finishes in March, I think. I can't remember if it's the beginning of March or the end of March.
Pierre?
Yes, what was the basis for the learning of the AI?
So do you mean what techniques are using on the autonomy engine? So they've trained their models in data that was from BODC, from campaigns on the area on the North Sea. I can't remember the exact project, but basically they took LiDAR data and fed and trained their models with that.
Thanks.
Are there questions? Yeah. I just see user as a name, so can you say
Yep.
who you are?
Yeah, hi there. Can you hear me?
Yes.
Yeah.
Yep. So sorry, Jeremy Sidbon from Alcimer.
Oh, hey, Jeremy.
Thank you very much, Alvaro. I don't know why it's a username, but from what you were explaining, you were saying that the backbone will be available for any user to use. What about the graphical interface? It looks like a lot of effort went through the abstraction of that concept. So what's the plan for that?
So the graphical interface is at the moment part of our bigger C2 system. Our command control system is not open source yet. Our intention, we're trying to find a way, is to make all or almost all our C2 open source. So I hope some news during 25 on that.
Okay, and before even getting it open source, could it be just available to other users?
Yeah, that bilaterally we can discuss that. Jeremy, if you want to talk to us directly, I'm more than happy to that.
Yeah, definitely. I'm sure we've got a trail of email about that subject already, but I'll jump back on that.
So for context, Jeremy, who works in Alzheimer, was involved with us on the beginning when we did the concept of the backbone. So actually, we came with a concept because between a back and forth between him and me. So yeah, I can't take all the credit on the idea. A lot of that came from him.
Come on, it came from you. Thank you very much, Alvaro.
No problem, Jeremy.
Thank you. Are there other questions? Other comments? Other, how do you say, some applause?
Or any other business?
Or any other business? Well, no, I think it's good to see the next steps. You're saying that it's just kind of as well a demonstrator of much of things bigger to come. So it will be good to see how it will evolve. And yes, Pierre, you have a.
Yeah, I would like just it's more a question to the audience. I would like to make a little survey.
Yeah.
Can you raise your hand if you want to, if you would like to use such a system established as a service?
Oh yeah.
We have 2 minutes. Yes.
Yeah.
Okay. 1, 2, 3, 4.
And for those who have raised their hand, if you want a small comment. Okay. Let's see, people are leaving.
Okay, thank you.
Okay.
Okay, so I have just a comment. I cannot raise my hand. I don't know why, but
Okay.
of course I'm interested also, and I'm also interested to know how we can also adapt this for our gliders. And also, well, I want to thank also Lucas because it's very, very interesting what he's doing. And yeah, we have to think about how we can apply also this for other kind of user. Yeah, thank you very much to you both.
So ours, so I said a lot of it is going to be open source. So we have spent a lot of time on integration of systems. I hope we can also release the SFMC adapter. So basically would allow you to take a backbone and connect it to your Slocum gliders. We're thinking on developing a sea glider adapter. So it can work with sea gliders, but the architecture is, I mean, the whole idea is that anyone can take it and develop their own adapters if you have the skills. In terms of the AI itself, that would be a question for a bilateral conversation with the Oxford if they want to. I don't think they're going to release it open, but you could use any other autonomy engine. So while the digital twin itself, without Oxford, you wouldn't be able to replicate all of it. You could do the same at a different area if you're collaborating with a different institute developing AI. I think the future will automate other things. At the moment, this is just changing waypoints, depths, and I don't know if anything else. Ben, which is I think he's still on the call, and we can tell us more. I see in the future will automate more things, and that would be based on different operational constraints and requirements. But this is a small step forward.
Well, I think that concludes the session, showing that there's a lot of possibilities. I would like to really thank Lucas and Alvaro for the presentation and for the interesting work. And it looks like it's going to start some collaborations, or at least some discussions, which is the aim. And on that note, I thank you all for joining. I wish you a nice winter break and holidays. And we'll meet again in January, and have a nice evening. Thank you all.
Bye-bye. Thank you.
Thank you, everyone, for presenting. Bye-bye.
Bye, thanks a lot.
Thank you all for